Yeah, yeah. So, in today's brief talk, in this lecture, we'll try to discuss various aspects of scientific payloads for space exploration, not only the solar system exploration, but space exploration at large. And we will have two kind of discussions why solar system exploration studies are being done and how it is being carried out using scientific payloads. And particularly, we'll discuss with photographs and videos the details and development of scientific payloads used for space exploration studies. And as we know, space exploration is the use of, knowledge of planetary science, astronomy, physics, and especially the cutting edge space technology to explore the outer space. So we'll begin our discussion with, what are the scientific payloads? Basically, they are the instruments designed to collect the data from, remote platform from for scientific experiments in order to increase or enhance our understanding about universe and solar systems. The basic primary benefit of these payloads are the payloads which are put on the spacecraft can go to the very far distance, which allow us to collect data and perform experiments in very harsh and challenging environments that are otherwise inaccessible to humans. There are various kind of payloads one can think of. The main one are scientific payloads, which are people do observations through these instruments. Communication payloads, which are used for far distance communication, data exchange, navigation to navigate the spacecraft and instruments. Human support payloads, that means they are used human support payloads and cargo payloads. They are being used for manned mission for life support, the keeping environment quite safe, and various kind of spare parts of you know spare parts which are being taken to the space station and those kind of missions. But today's discussion would be, we'll be discussing about scientific payloads. Basically, development of such kind of technology or instrument started with the first launch of satellite Sputnik in 1957. Now it has been more than 6 decades. These technology and scientific understanding has advanced to a quite a greater height. However, this process of designing space payloads or instruments, they look quite exciting, but they are very challenging and difficult because they have to work in very extreme and harsh conditions without direct intervention from humans. And these kind of instruments, they go through several stages of development, starting with a paper design or functional design to an instrument with various testing with proven performances, and which ultimately flies on the final finished mission. So there are various stages. We'll try to discuss with example what are those. Very major stages of development of any space science instrument are, if you can see the right hand side photographs where we develop these scientific detailed specific instruments. They are being designed by various institutions. One of that institutions, premium institutions, is our Space Application Center SAC, Ahmedabad, which is a premium lab of ISRO, which is indulged in such kind of scientific instrument development for Earth observation, planetary sciences, or space exploration studies. So various institutions around the world, they develop these instruments and they deliver it to the spacecraft for its integration into spacecraft. The second stage, you could just see, these are not the exact stage, these are very rough major steps I am showing. These scientific instruments, they are then being integrated inside this kind of satellite bus. And with this satellite system itself, various tests, they undergo with all the subsystems, because they have to see the performance of various commands, telemetry, power, thermal and mechanical properties with their extreme limits also. So once this satellite is ready, they are being transported to the, let us say, for example, here in India, we transport it to Sriharikota, our launch pad of India, and they are being integrated into the rocket system. And they are then being, on the specific date and time, they are being launched through our GSLV or PSLV vehicle. Once after the launch, the scientists or engineers who have developed or designed these instruments, they are the main persons who have developed that instrument. They know how to operate it within flight through various commands and various modes. They operate through our telecommand and control station, and they try to observe that particular instrument for specific scientific purposes. So these are the major stages through which this instrument goes through. The major themes where these kind of instruments are being discussed generally are, one can say, planetary sciences, astronomy and cosmology, and heliophysics kind of, themes, where we understand the astronomy, cosmology are study of objects or processes or of phenomena in space, and cosmology is the study of origin of universe and its evolution, and we observe it through various instruments. We'll see some of those examples. Planetary science, those studies, they include the study of various planets, including our own Mother Earth, and celestial bodies, moons, asteroids, comets, etc., and planetary as a system. Planetary systems as a system of systems we study within planetary science. And heliophysics, which is nothing but a comprehensive study of sun, solar system connection, understanding of Earth space environment, or various phenomena in space which is influenced by various star like sun. So that's why people say it is a combination of, let us say, heliosphere, which is solar physics, space weather studies. So people use various scientific instrumentation for this kind of scientific exploration study. But what do we observe in university? We would like to make instrument, but what do we observe? So these are very major, components, major, important elements which we generally would like to observe. First one is electromagnetic radiation through, remote sensing, method. Without touching or without going into those, about object from far distance, we try to understand the properties of certain object through photometry, spectroscopy, or polarimetry, where we try to understand the radiance or radiation from the object, what is its spatial distribution, how that radiation is distributed as a function of wavelength or frequency, and what kind of scattering and absorption properties are being observed through some of the polarimetric observations. Second category are particles, which are somewhat, one can say, in situ within that medium. One can observe various particles, either it is nuclei, cosmic rays, electrons, protons, and neutrons, because they emerge from various processes, and one has to observe this kind of particles. And very peculiar kind of waves, gravitational waves, considering the fluctuation space and time. So we'll one by one we'll try to see how we observe and with which instruments we observe electromagnetic radiation, particles, and gravitational waves in subsequent slides. So we'll start with the electromagnetic radiation. That electromagnetic radiation, which is, one can think of having various wavelengths or frequencies, starting from radio waves to very high frequency X-rays and gamma rays, which is covering from very low to high energy levels also, which are prevailing in solar system. And one can observe this kind of electromagnetic radiation with various, probes. And we all know electromagnetic waves, they are radiated from a form of a wave resulting from the motion of electric charge and magnetic field, which are perpendicular to each other, and they are the main primary mode of observing the very far distant universe. And as we discussed, it can be observed through imaging, spectroscopy, and polarimetry. So how one can observe this? We'll try to see imaging, spectroscopy, and polarimetry. As the name suggests, first imaging is to image certain objects or media, how much the light is being spatially distributed, how they are being actually propagated in various mediums. And once we observe through cameras or spectrographs or spectrometers, one can have this kind of observation. Just a simple examples of some images, beautiful images of Hubble and James Webb are shown, which are being actually observed through imaging and photometry. After imaging that, we observe these kind of objects at different wavelengths. Why different wavelengths are important? Because the wavelength which is having different kind of frequencies, and the wavelength numbers, they infer information about various phenomena occurring at different energies and different levels. And if we observe, like what you see on right hand side, the sun is observed at various wavelengths of very high, moderate wavelength to very low wavelength of 130s, 90s angstrom to certain 1700, 1800 angstrom. And you could see how these information of various levels or various media of sun, its surface, its corona, they are being manifested as a function of wavelengths. So this is the beauty of multi-wavelength observations. And if you do it through certain vantage point, it can give you very detailed observation of some of the processes, some of the objects which otherwise would have not been possible. Or these are multi-wavelength observations where the universe, we know universe presents a wide range of extreme environments, from very cold to very hot background, which can be probed from radio to gamma ray spectral regimes. And basically it provides you the different and unique information about varied properties of the target and the medium. This is a same sample of space which is being sampled at various frequency levels or various frequencies, which is around radio frequencies to gamma rays, which actually bring out detail of various levels on various information about this particular sample. Obviously, the spectroscopy, which gives you how radiation from any object is being distributed across frequencies, because depending upon the rotational, vibrational, processes which are being occurred, which occur at various spectroscopic level, it can give you a unique information about emission processes, chemical composition, temperature of certain targets, and which generally gives continuum or line emissions. We are not going into great details, but the fundamentals, one of the spectral distribution laws or two laws which are very, very important, we'll try to see simple law. One is called Planck's law and another is called Wien's displacement law. They are very, very important as far as remote sensing of any object is concerned. This we can just briefly discuss. Planck law describes the spectral distribution of electromagnetic radiation emitted by black body at temperature T, which is nothing but 2 pi hc square upon lambda raised to 5, 1 upon e raised to hc upon lambda kt minus 1. And you put a temperature, let us say 300 Kelvin, and then change the wavelength at lambda, you would get a distribution of radiation, and which can be seen for varying temperature, how envelope of spectral radiance are charted out. You know, this pink color provides you spectral distribution of 300 Kelvin object, black body object, and then 500, 750, 1000, 3000, and 6000, which is somewhere around. So if we see the temperature of Earth, by and large, if we consider it to be approximately 300 Kelvin, the Earth by and large emits its radiation somewhere around this particular, envelope, with the peak emission somewhere around 9.6, 9.7, 9.8 micrometer. So if one has to do thermal remote sensing of Earth, he has to do remote sensing somewhere around 9.8. But if I wish to see sun from remote sensing platform easily, it has its peak somewhere around 0.5 micrometer. So for 300 Kelvin, it is 9.8. At this particular 6000 Kelvin, it is somewhere around 0.5 micron. And as a function of temperature, the peak shifts systematically towards lower wavelength as temperature increases. And this translation of peak is manifested as Wien's displacement law, which is shown here. So one can use these laws to understand what kind of observation we have to observe at which temperature and which wavelength. And I have to, if I would like to observe a planetary body of 600 Kelvin, I should design my instrument with a certain characteristics. If a temperature is quite high, I have to design according to that particular thing. So for example, if I need to observe Earth, which has a temperature somewhere around 300 Kelvin, we obviously have a window around 10 micron. Mars, which has a temperature range of 130, 140 Kelvin to 280 to 90, it has to be done at specific temperature, specific wavelength region of higher, somewhere around 13, 14 micrometer. And if we talk about Venus, which has quite a large temperature range, it has to be observed by considering these temperature distribution. So these are the consideration. If we understand the basic physics, you have to consider it for the design of any scientific instrument. The beautiful example of a black body radiation law was actually exploited by these two gentlemen, Dr. Smoot and Dr. John Mather, who have designed an instrument called FIRAS on an instrument, space-based instrument, COBE, Cosmic Microwave Background Experiment. And they measured the CMBR, the residue, humming of the so-called initial days of universe. And there they actually, what they did was they understood the black body radiation distribution of temperature equivalent to 3 Kelvin, which is nothing but somewhere around millimeter scale. And they designed their instrument in this particular wavelength region, and they could detect the CMBR, which is very, very, feeble signal in the universe. And they actually received the first of its kind, Nobel Prize in physics using satellite-based observation. So if we understand the spectral distribution, design scientific instrument, it can fetch Nobel Prize as well. That is the point to be noted. one of the beautiful instruments in the history of remote sensing or space, exploration studies is Hubble telescope, which had various cameras, spectrographs, and interferometers, which observed universe at a or various, they sent beamed beautiful image of various, images of space, which has revolutionized the understanding about the universe. And one of the examples, if you just see the spectrographs, because spectrographs, breaks down various lines, they break down their components and how generally prism splits the white light into rainbow. And by these characteristics, it can give you the understanding about temperature, density, chemical composition, and various observation. Here, I'm showing a space telescope imaging spectrograph STIS, which has observed a massive star pair, and they could show the presence of helium, argon, iron, nickel kind of species, and which gives you an important clue about the processes which are going on in some of these kind of objects. The next one was is beautiful, one of the unique kind of telescopes, that is James Webb Space Telescope. Most of you are aware of these. They actually have a primary mirror which consists of 18 hexagonal mirror segments, and which gives you a 6.5 diameter equivalent mirror, which is compared 2.5 to 3 times of Hubble telescopes. And it gives you detailed, very high spatial resolution and beautiful observation through middle infrared, near infrared observation through spectrometer, camera, and spectrograph, and which gives you finer details compared to any other space telescopes which had given earlier observations. This is the example of, one of very beautiful image of, black hole, which was observed, supermassive black hole observed at the center of galaxy M87, because around 100 years back, black hole was just an equation. And somewhere around, last 20 years or so, and especially in 2019, the first ever picture of this closest supermassive black hole at the center of galaxy M87 was imaged through processing of thousands of image, which is, around 26,000 light years away, which was captured through Event Horizon Telescope. And you could see the emission from hot gas swirling around the influence of very, very strong gravity near the event horizon. And these kind of observation, they are being observed through a technique called very long baseline interferometer, which is called VLMI, and which gives you almost virtually Earth-sized dish, which provides you very detailed resolution by putting these instruments at various geographical location. You could see left-hand side of small, view graph, and this kind of unique observations were made. After spectroscopic and that observation, the very detailed, important hidden information one can get it is through polarimetry, which is basically the measure of polarization of the light, which can give you information basically about this scattering. Typically, scattering induces the polarization, or many times emission mechanisms that also cause polarization, and this gives you some hidden information which otherwise would have not been observed through the intensity measurement. This example of polarimetric X-ray polarimetric observation, where you could see the large image of IXP combined with Chandra telescope observation in blue and optical light in golden color with Hubble, which basically observe a supernova remnant. And these lines which are basically graphical lines which come from IXP polarization measurement, which researchers say they show the direction of magnetic field across the regions of this remnant, which provides you very some of the secret information through polarization as well. The last part is through observation of particles. So solar winds and particles within solar system. Generally, solar wind is a stream of what we understand, stream of charged particles released from upper atmosphere of sun, and which is called corona, and consists of electrons, protons, alpha particles. So those kind of ions and those kind of particles are being also emitted, are being also thrown out of various systems, which have to be also observed. And that direct detection of these kind of particles are possible through which can give you understanding about solar winds, the corona mass ejections, CMEs or atmospheric processes, and which can give you information through instruments called mass spectrometer. The mass spectrometer, what does it do? They detect the particles created by various processes, as we discussed, and it converts molecules into ions, and under the influence of electric field and magnetic field, these ions are manipulated in presence of these fields, and they are being basically based upon their mass to charge ratio, they are being separated, and understanding about the mass, charge, temperature, velocity distribution can be observed about the particles. The another important field which people do is gravitational waves, which are the ripples in space time, which are caused by some of the most violent and energetic processes in the universe. And as Albert Einstein predicted, I think in 1920s, that in his general theory of relativity, where his mathematics showed that some of massive and accelerating objects like black hole and neutron stars orbiting each other would generally disrupt the space-time in such a way that this kind of waves they undulate the space-time and propagate in all direction away from the sources. So what these are some of the latest frontiers in astronomy, where people observe mergers of very big and heavy objects, and which provides the ripples in space-time. And some interferometric, high sensitive interferometric instruments are being used for observing this kind of phenomena. And researchers have planned a instrument called LISA, laser interferometer space antenna, as a combination of three systematically revolving satellite, which would provide interferometric long baseline and interferometric measurement to observe the gravitational waves. So now, within last 5-7 minutes, I will try to show you some of the examples of remote sensing instruments, how they are being designed, and what kind of observations, scientific observations they show you. And they are working at various wavelengths. First and foremost is our own Mars color camera on Mangalyaan 1, which was basically RGB camera. You could just see the size, mass, and power of this instrument. So whatever space instruments are to be designed, it has got great constraint of only small size, very small weight, and very small power. and which provided beautiful images of Mars. I will show you. This is a first and last image before leaving for the Martian, transient orbit on Earth orbit. MCC took this Earth image. This is the first Mars image on 24th of September 2014, the first image of Mars, which was taken by this camera. This is a global various pictures in 2014 MCC camera has taken. This is one of unique pictures of Valles Marineris, one of the largest, canyon system of 4,000 kilometer in length and 2,000 kilometer wide and 7 kilometer deep, which gives you a various idea of various clouds. They are being actually seen in this image, or Martian clouds as seen in Arsia Mons. So sitting at Earth, sitting at Bangalore, at our deep space network, this kind of information you get on your desktop through some of the scientific instruments which were designed. Then optical and infrared imaging spectrometer, like MOM thermal infrared imaging spectrometer, which worked in thermal regime, or JWST, as we discussed, one of the spectrometer which works in middle infrared, wavelength range of 5 to 28.5 micrometer region, which gives unique observations. Hubble also had this kind of information. Or X-ray imagers, where they are quite, sensitive to solar flares and gamma ray burst, phenomena. So these are the instruments which were there on AstroSat, SXT, or some example of NASA. I don't want to go into detail. This is just for your information that as a function of various wavelengths, one has to design these kind of scientific payloads or instruments, keeping in the mind the wavelength regions, how to observe it, what kind of unique observation it would provide. Then X-ray spectrometer, which gives you elemental abundance or composition of plasma, which is very, very important for understanding the supernova composition or solar flare composition. So Aditya L1 has these Solaxes and Helios, soft and hard X-ray instrumentation, or NASA and JAXA had various instrumentation. Some of them are shown here. UV imaging and spectrometer, which provides very chromospheric and coronal information about sun surface. So AstroSat, we had UVIT, and one of very unique instrument of NASA, Cassini. There are many instruments. These are two of these instruments I am showing. UVIS, which gave us spectacular information about very planetary environment. And obviously over Hubble and other instrumentation, this kind of spectrometers are also situated or sent. Coronagraphs, which are nothing but optical devices which are used to study very, very faint, regions surrounding very bright stars or sun, so that you could understand very detail about some of those processes. Aditya L1 had VLC or has VLC, visible emission line coronagraph, or SOHO also had, NASA SOHO also had this kind of observations. I will show you few in situ observations, how it has to be done. It has been done by some instrumentation. One is magnetometer, which measures the direction, strength, and variation in magnetic field to provide the detail of magnetic field around Earth, Sun, and other planets. Aditya L1 has its own magnetometer, and earlier Voyager and various instrumentation or space probes had this kind of in situ measurements, magnetometers. Langmuir probe, which is one of the very famous or very popular instruments, which measures the electron density, electron temperature of plasma, plasma potential, electron energy, and distribution of these kind of, species, which provides you understanding about the Earth ionosphere and environment of other planets also. In future, we will have also, ISRO will have a instrument on Disha, where we have a high frequency Langmuir probe, and Disha will be a future instruments, pair of instruments will be sent. And MOVAN and other NASA's mission also had a lot of instruments at this Langmuir probe. As I said, it is a popular one. Retarding potential analyzer RPA, which are particle analyzers, which basically observes the charged particles through various, engineering, and the Aditya L1 and other instrumentation also had this kind of instruments. Mass spectrometers, as we discussed, it's also very popular, very important instruments which measures the mass to charge ratio of, neutral particles to use to understand various materials, including gases, liquids, and solids, and various space probes had. MOM also had instruments called, very popular instrument called MANCA from ISRO, and there are various instrumentation on MOVAN, Venus Express, which also had this mass spectrometers. The last section, just 2 minutes, I would like to just show you various components. Generally, people have to, or researcher have to understand in designing a space instrumentation. I will take electro-optical instrument as an example, where you need to have observation of radiation through certain celestial objects, collect it through optics, and then detect it and read it through electronic systems, where you obviously have to have electro-optical imaging instrumentation, which will have focusing optics for light collection, dispersion system, detection system, electronics, and mechanical assemblies. So, and for space-based probes, you need to have low weight instrumentation with low mass, very good thermal stability, very good optomechanical sensitivity with less coefficient of thermal expansion or moisture expansion. Should be very, very lightweight, which would work. This material would work in very harsh environment also. And it can use refractive, reflective, or some, catadioptic kind of instrumentation for which can cater from very large optics to very, small optics having less temperature, less weight and mass. And the last one, but not the least, is the detector system. There are various kind of detector system. As a function of wavelengths, one can observe through silicon photodiode or in various kind of, infrared observations, and, thermistor bolometer, MCTs, and various kind of, pyroelectric instrumentation. So, in summary, I would again come back to the major, to just summarize the total talk. One has to develop specific instrument depending upon the problem and scientific object to be observed. It has to be integrated, it has to be launched, it has to be monitored, it has to be ultimately operated through your specific plan with a very, very precise management and planning, which would ultimately give you improved scientific understanding about celestial objects and universe, which pave the way for the discoveries. So this is my last slide, where, people say that one can easily make instrument, but the difference between simple instrument, which is an affordable and scientific sound instrument, sound mission, with not a great mission, is the difference between development of cutting edge technologies. That means recent advanced instrumentation development and basic physics, engineering, discoveries of materials, and those go into development of scientific instrument, and that gives a great, way for developing beautiful scientific instruments. So I thank you. I acknowledge Chairman ISRO, Director SAC, Director SPO, Dr. Praveen Kumar from SPO IRS team, and obviously all the participants who are joining this particular, who have joined this session, and my team members here at SAC, specifically Asif and Manish, for all the help. Thank you. And I stop here. Thank you.